an AI-generated post for your viewing pleasure. Unlocking the secrets of Babbage's analytical engine, a journey through early computing. What if I told you that the foundation of modern computing might already have been laid over 175 years ago? The analytical engine, conceived by Charles Babbage, was more than just a mechanical curiosity. It was a precursor to today's universal computers, packed with unexpected potential and unconventional programming models that could still inspire innovation today. Before we dive deeper into Babbage's work, let's take a moment to consider how the analytical engine relates to today's technology. In this discussion, we'll uncover its innovative design elements and how they paved the way for modern computing as we know it. Welcome back to the channel. Today, we're diving deep into the innovative world of Charles Babbage and his groundbreaking creation, the analytical engine. You might think of early computers as straightforward machines for calculations, but Babbage's design reveals a rich tapestry of computational concepts that hint at capabilities and structures we still rely on now. With ideas that might seem familiar from modern programming, let's explore how the analytical engine holds keys to understanding the evolution of computing. Picture this. In the 1830s, Babbage envisioned a machine that could perform complex calculations automatically, setting the stage for what we now know as computers. His work didn't just stop at basic arithmetic. It encompassed many foundational concepts that would later become central to computing, such as conditional branching and data manipulation. This exploration connects Babbage's historical context with our modern expectations of machine efficiency and capability, proving that innovation has long been rooted in the creative struggles of early scientists and engineers. Now, let's briefly set the stage about what we'll be talking about today. The analytical engine represented a significant leap in mechanical computation, incorporating features like a mill for processing data and a store for memory. To fully appreciate its complexity, it's important to understand a couple of terms. Indirect addressing allows a program to use variables to reference data locations dynamically rather than being shackled to fixed addresses, giving programming added flexibility. Additionally, conditional branching refers to the ability of a program to execute different paths in its operations based on conditions, creating a more adaptive and intelligent computational process. With this foundational knowledge, we can better grasp how Babbage's unusual programming model not only utilized gears and mechanical features, but inspired structures we continue to use in the world of computing today. We'll look at how these early innovations reflect the programming practices we consider standard now, and the parallels that emerge through the ages. Next up, we'll break down the technical contributions of the analytical engine, focusing on the key elements of its design and functionality. From its separation of processing and memory to its innovative use of operation cards, let's delve into how these features set the stage for future computing developments. The analytical engine operates with a fascinating dual architecture, a mill which serves as the processor and a store, which represents memory. This separation is surprisingly akin to modern CPU and memory systems, where tasks are distributed between distinct units for efficiency. But there's more. Babbage's design incorporated indirect addressing, a feature that links the A more closely to contemporary universal computers than previously thought. A key realization here is that Babbage's use of fixed addresses for operations showcases a unique approach to handling data within the AE, mirroring practices in today's memory management strategies. What's particularly remarkable is how programming the A wasn't straightforward. It required multiple pairs of cards for each arithmetic operation, leading to inherent inefficiencies. For instance, the operation of addition necessitated 3 pairs of address cards, making the process cumbersome and highlighting the limitations of Babbage's design. However, amidst this complexity, Babbage included the capability for conditional jumps and loops. This ingenious mechanism can be likened to the programming principles we now standardize, where loops allow for repeated tasks, reinforcing that iteration was considered as far back as the 19th century. Imagine coding in a time when every operation required meticulous attention to card sequences. And if you've ever thought about loops in programming, you should be intrigued by Babbage's inventive cycles of cards' mechanical loops, long before modern language constructs. Just as today's languages allow for escalated automation and programming, Babbage's design ensures that efficient operations could repeat in a structured manner. This is a clear demonstration of how principles of iteration were not only envisioned then, but also showed foresight into how automation would evolve over the centuries. The acknowledgments of such structures invite us to reconsider their historical contributions and recognize their continued relevance in modern computing. Now that we've understood the technical aspects of the analytical engine, let's connect these innovations to a broader context. We'll dive into how these contributions resonate in current computing practices and what we can learn from Babbage's engineering genius. Now let's connect the dots. We know that contemporary computing heavily relies on abstraction and efficient memory management. Babbage's use of fixed addresses and subroutines to handle indirect addressing showcases a belief in the significance of organized information flow concepts current programmers grapple with daily. The relationships between the needs of early computation and today's programming practices illuminate how foundational programming structures can emerge from restrictive designs. Interestingly, the idea that the analytical engine could emulate a Turing machine with a finite tape stands out. This realization urges us to reconsider the potential computations of early devices and recognize that Babbage might have been more visionary than we give him credit for. However, it's crucial to acknowledge that while the theoretical framework is intriguing, the real-world application of these concepts raises significant concerns. The complexities involved in managing punched cards and the physical limitations of the hardware are significant hurdles that are not adequately addressed in the theoretical exploration. Furthermore, the paper notes that the proposed method for implementing indirect addressing is described as very inefficient, which poses a major barrier to practical use. The reliance on fixed address numbers without a robust system for indirect addressing limits the machine's ability to handle complex data structures effectively. This inefficiency complicates programming and makes it unsuitable for real-world applications where speed and efficiency are paramount. Without practical demonstrations or simulations to support the proposed programming techniques, the significance of the findings is limited. Ultimately, while the theoretical exploration of indirect addressing in the analytical engine is a valuable contribution to our understanding of early computing, the lack of practical evidence and consideration of real-world constraints diminishes the overall impact of the research. This oversight serves as a reminder that the journey from theory to practical application is often fraught with challenges that must be addressed to realize the full potential of innovative ideas. In conclusion, the analytical engine is not just an artifact from the annals of history. It is a beacon highlighting our ongoing journey into the realm of computing. The ingenuity captured within Babbage's machine reminds us that the core ideas of programming conditional jumps, indirect addressing, and iterative processes have deep historical roots that shape the technology we take for granted today. So, the next time you sit down to code or you're working on an algorithm, remember the meticulous efforts of Charles Babbage. His early experiments with computation paved the way for the future of technology, and there's still so much we can learn from his vision. Don't forget to like, share, and subscribe for more deep dives into the history of technology that shapes our world. Until next time, keep exploring the extraordinary connections that bind the past to our present.